Today I'm going to go over the Chapter 5 Comprehension Check. So for the Chapter 4, we focused on ionic compounds. In Chapter 5, we're going to focus on a different type of compound called covalent compounds. So when we talked about ionic compounds contain a metal and a non-metal. So we said that they contain, on my periodic table that is not finished, but a yellow metal and a purple non-metal. And when an ionic compound forms, what happens is one compound is giving electrons to another compound, and that one is taking it. But today we're going to focus on covalent compounds. So when you make a covalent compound, these are compounds that actually share electrons in order to get 8 valence electrons. So we're going to look at, with covalent compounds, these are going to be using our non-metals, so my purple part of my periodic table, to make these covalent compounds. Now, please remember that my non-metals also include hydrogen and helium that are over here, and then all these purples. And we're going to do some examples of making some compounds with these. One of the first terms, though, that you need to be introduced to is called a homonuclear diatomic. And if you look at the word, homo means the same, and di means two, and atomic is atoms. So basically the same two atoms. So homonuclear diatomics are atoms that essentially do not like to be alone. They are always either in a compound with another element, or if they're by themselves, they're with like another one of them. And so what I mean by that is, let's take hydrogen. If you have simply hydrogen, it's not ever going to be alone. It is going to always be bound with another hydrogen, and you would write that like compound this way, or we would write an H2. The reason it doesn't like to be alone is, if you'll remember from Lewis structures, hydrogen has 1 valence electron. And so what these 1 valence electrons do is they will pull together to make this pair in the middle. The elements that are homonuclear diatomic, there are 7 of them, and they essentially make a 7 on your periodic table. They include hydrogen, and they come over here, and this is where you get the 7. You go nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. So you can kind of see this 7 shape that's made on the periodic table. And for the 7th element, you add in hydrogen. And so these are all compounds that, if they exist just by themselves, they're going to be bonded to another one of themselves. So like, you are not going to have 1 chlorine, you're going to have 2 chlorines. Comprehension check question number 1 says to draw the Lewis structure for bromine as it occurs naturally, and to use a dash for the bond. And so bromine is in this 7 of the homonuclear diatomics. And so naturally, you're not going to ever find just bromine. It is going to be in a compound, so that's what we're going to draw. So as we make these compounds, let's remember that we have what's called the octet rule, which tells us that atoms like to have 8 valence electrons. This is with the exception of that hydrogen that I just drew. And so they're going to bond so that they have 8 electrons. Now, ionic compounds are going to be giving away or taking electrons, but we are talking about covalents, which are all non-metals down there, and they are not giving away or taking, they are going to be sharing electrons. So if we're looking at bromine, let's figure out how many valence electrons it has. If you'll remember from the previous chapter, you were able to look at the group it is and use that to determine its valence electrons. If you'll remember, this was group 1, group 2. We didn't count those when we counted the columns because these don't follow the rules. 3, 4, 5, 6, and 7, and 8 valence electrons. So bromine is in group 7A, so it has 7 valence electrons. So here I have put 2 bromines because bromine is a homonuclear diatomic, so I'm going to naturally have 2 of them. And I have put red dots to show the electrons on this bromine, and there are 7 of them, and so this would be a Lewis structure of bromine. And then there's the same thing for this other bromine. Now, as I have drawn them, I have put the layers on the same like sides as each other. And so in a covalent compound, what is going to happen is these layers of electrons are going to basically come next to each other to make a pair. So that way this bromine would have 8, and so would this bromine. And this is a covalent compound. They are sharing these electrons so that they have 8 valence electrons. Now, the book asks you to draw this Lewis structure, putting a dash in the middle to represent a bond. And so when you have a bond with these, you would just draw a line in the middle. So this is the Lewis structure of bromine in its natural state. Comprehension check question number 2 has 4 parts to it, and it asks you to draw the Lewis structure for 4 different covalent compounds. So for part A, I'm given H for hydrogen and Cl for chlorine. And so the compound I'm going to make is going to use a hydrogen and a chlorine. One of the first things I can do to know that this is going to be a covalent compound where they are sharing electrons is I can confirm that both of these are non-metals. And so on my periodic table, they're both purple, so they're both non-metals, so this will be a covalent compound. Now, I am going to go ahead and do the Lewis structure for each part of the compound before you make the bond in the middle. So hydrogen is in column 1A, so it has 1 valence electron, which I am representing with my 1 red dot. Yes, you can put it up here, but as far as making the bond goes, we're going to put it next to the chlorine. Now, chlorine is in group 7A, so it has 7 valence electrons, so you're going to fill in. If you'll remember, as you first fill in your electrons for your Lewis structure, you come in and you put them separately first, and then you go back around and make pairs. To make these now in a compound, now remember, hydrogen has its own rule where it makes 2 to make a satisfied electron, like 2 valence electrons, and then chlorine follows with all other atoms where it wants 8. The reason that hydrogen only wants 2 is hydrogen has just 1 shell of electrons, and that first electron shell is that s orbital, and it can only hold 2 electrons in that 1s orbital. After that, every other one can hold 8 valence electrons. So I can see by looking at this, the way that we have the electrons placed, that the hydrogen and the chlorine can each share their extra electrons so that hydrogen has a 2 valence electrons and chlorine then has 8. And when you draw the Lewis structure, you're going to draw a bar to represent the bond. For part B, it gets a little more confusing looking because we have 3 different elements and we have 5 atoms that we're making in this bond. So we're going to start with carbon. Traditionally, when you have carbon, carbon can make, if you'll notice, its valence electron is 1, 2, 3, 4. So it has 4 valence electrons. Carbon is frequently going to be the middle atom of your compound. So if you're looking at this and you're like, I have no idea where to start, but it has a carbon, put carbon in the middle. Now, since carbon has its 4 valence electrons, I'm going to go ahead and add my electrons. Now I'm working my way around the carbon, and so I don't have any pairs yet. So the other one that I have is I have a hydrogen. Now this 3 lets me know that I have 3 hydrogens. So I am going to place them around my carbon, and each hydrogen has 1 valence electron, and I'm still going to use red to represent that, so I hope that doesn't get confusing. So I'm going to place them around. It does not matter where you put them around this carbon. Just use your 3 hydrogens, and each hydrogen has a valence electron. And then the last element that we have is bromine. And if you'll remember, bromine is in the column for 7A, so it has 7 valence electrons. I'm filled in my 7 valence electrons around bromine. So what is happening here is this hydrogen and this carbon, they are sharing electrons to make that covalent bond. And the same is happening at all 3 of these carbon hydrogens where you have all these extra electrons. And so at the carbon bromine, these electron pairs also are making a bond. And so this is going to be your Lewis structure for CH3Br. So for comprehension check question part C, they are seriously trying to trick you up on this one. Because let's look at this compound. I have potassium, which is a metal, and I have oxygen, which is a non-metal. So when I have a metal and a non-metal, this is not a covalent compound. This is an ionic compound. So they are sticking this one in here to see if you're paying attention. For this one that they've tried to trick you making it ionic, I have 2 potassiums and an oxygen. So an oxygen, if you'll remember, is in the column 6 valence electrons. Since it has 6 valence electrons and this is ionic, it is going to want to be taking 2 more electrons so that it has a full electron shell. I'm going to draw oxygen in the middle. And do I expect you to instantly know to do that? No, but you're going to learn that you're going to split like the potassiums up. As you see these, you'll get more familiar with them. So if I draw my 6 electrons around oxygen, I'm just going to put it this way, and then potassium, being in one column, has 1 electron here each. This is not a covalent compound, which means these do not share to make this line bond. What actually happens is oxygen just takes these electrons to it, and since oxygen is taking in electrons, it gets a charge of 2 negative because it gained 2 negative electrons. This one lost 1, so it gains a charge of positive, and this is a charge of a positive 1. So this is technically what the Lewis structure would look like for this ionic compound. So if it tricked you, it's because we have a metal and a non-metal, and so it's ionic. For a compound in part D, we have SF2. And so with SF2, we have sulfur and fluorine, and both of these are non-metals. So this one is not to trick you. They are just trying to get you to draw the Lewis structure for a covalent compound. Now, I have 1 sulfur and 2 fluorines, so I'm going to try to put the sulfur in the middle and the fluorines on each side. And if you'll realize that sulfur has 6 valence electrons, and so I'm going to put my sulfur like this. I can put my sulfur like this with the 2 valence electrons empty on this side, or I would accept it like this either way. As far as to figuring out what's the best way to draw this, we'll get there better on in the chapter, and so either way is acceptable. And so then you have your 2 fluorines, and they each have 7 valence electrons. Now I don't have enough of my red dots over here to do 7 for each fluorine, so I'm just going to draw in pink dots. And so when you put in your 7 valence electrons along fluorine, you can see that the fluorine and the sulfur are going to share an electron to make a covalent bond here. And the same is going to happen here. These are going to share, and so when you do a Lewis structure, you draw a simple line. So this is the Lewis structure for SF2, and it has a lot of valence electrons out there. So when we get into comprehension check question number 3, we're going to get into some more complicated Lewis structures, and you're going to be introduced to something called a double bond and a triple bond. And so one of the best ways for me to show you this is by example. And so question number 3 gives you a carbon and an oxygen, and it asks you to draw the Lewis structure. Well, carbon is in group 4. It has 4 valence electrons. And oxygen is in group 6, and oxygen has 6 valence electrons. Now, both of these elements are non-metals, so they're not trying to trick me here with an ionic compound. This is going to be a covalent compound. So let's start trying to put in some bonds here to see how we can make this compound. Now, this oxygen and this electron next to each other are going to come together to make a bond. That one's pretty easy to be seen. Simple like that. But if you'll still look here, we still have an electron on oxygen that is not bonded and an electron on carbon. And so these are going to come together to make another bond. And so when these come together to make another bond, we're going to draw another line. And that is actually a double bond because you have 2 bonds. These can come together to make a pair. And so let's see how many. Now, if you'll remember, since this is a covalent, this technically represents 2 electrons. So oxygen has 1, 2, 3, 4, 5, 6, 7, 8 valence electrons there. So it's satisfied. But carbon would have 1, 2 in this bond, 3, 4, 5, 6. So carbon, in this case, if it was like this, is not, because it does not have a finished 8 valence electrons. So what actually is going to happen is one pair of these is going to come in here in the middle, and this makes another bond called a triple bond, and this puts 6 electrons in a bond. And so if there's 6 here, 7, 8, which would give carbon 8, or 6 here, 7, 8, it gives oxygen 8. And so for the carbon monoxide is how we are going to say this. You'll learn that later on in the chapter. It has a triple bond. So for part B of question 3, they're just making this have 2 oxygens. So we're going to draw this again. We're going to put carbon this time in the middle. We've talked about carbon, put it in the middle if you don't know where to put it. And I'm going to fill in my 4 electrons for carbon. And now I'm going to add in my 2 oxygens. I'm going to put them on each side, and I'm going to draw the dots, the electrons with them. And the oxygen has 6 valence electrons. You fill them in around. Now I have my carbons, I have my 2 oxygens, each with their valence electrons. So let's see how we can make these bond so that it is satisfied with each element having 8 electrons that they either have around it or that they're sharing. So clearly I can see that there's going to be a bond that's going to form right here between these 2 electrons. And the other one I can see right here is going to be these 2 electrons are going to be sharing. So now this gives me 1, 2, 3, 4, 5, 6, 7 electrons on each of my oxygen and 6 on the carbon. So what you're going to see happen is you're going to see this electron and this electron are going to like move up here and make a bond. And the same is going to happen over here. This electron down here and this electron up here are going to come together to make a bond. So let's check to see if we have 8 electrons on each element now. So it's like 1, 2, 3, 4, 5, 6, 7, 8 on this oxygen. 1, 2, 3, 4, 5, 6, 7, 8 are connected to this carbon. 1, 2, 3, 4, 5, 6, 7, 8 are on this oxygen. So this is carbon dioxide, the gas that you breathe out, and it has several double bonds in this compound. So now we're going to learn to name these compounds. And these compounds are named differently than ionic compounds. If you'll remember when we were naming ionic compounds, we just named the metal, the non-metal, and you dropped the ending on the second element and you added IDE. Now, that was easy for ionic compounds, but when you get to covalent compounds, you have to add prefixes. So when you're naming a compound, one of the first things you need to ask yourself is this ionic or is this covalent? If it is covalent, then you need to add the prefixes. So the prefixes that we use are mono for 1, di for 2, a dice is 2 sets, tri like a triangle is 3, tetra means 4, we're going to use penta for 5, hexa for 6. There are many more, but this is as far as we're going to take it for this class. So comprehension check question number 4 ask you to name this compound. Since we're naming this compound, we have 1 carbon, and the natural tendency is to pick the prefix and say monocarbon. The exception to the rule is if there is 1 of the first compound, you don't put the mono on it. But if there are 2, then you would put the di. But for the first compound, we're not going to list the mono. And now we have 4 chlorines, and 4 is tetra, so it's carbon, and we would say tetrachloride. And just like with ionic compounds, you drop the ending and you add IDE. Question 5 gives you the formula, gives you the name, and it wants you to come up with the formula. So silicon, now remember, it doesn't say monosilicon because if it's the first element, it doesn't have to have the mono, but I know that this is just 1 silicon. And monoxide is 1 oxygen. So this would be the formula for silicon monoxide. The next part of the chapter talks about trends in the periodic table. And you're going to see on your periodic table in the book, when they talk about trends, they actually take helium and they move it over here because the trends work better with helium over there. And so one of the first trends you get of a periodic table is called atomic radius. Atomic radius is simply just how big, the distance, the radius of the atom. So the distance from the nucleus to the valence electrons. And so atomic radius they have in your book, they say that it decreases as you go across and up. So in your book says as it moves that way, the radius gets smaller. So helium is gonna have your smallest radius, and I don't have it on my periodic table, but Fr or francium down here at the bottom left is going to be your largest atom that you have on the periodic table. The other trend that we have is something called electronegativity. And electronegativity comes into action when we have these covalent bonds. When we have two atoms and they're sharing electrons, not all atoms are pulling equally on this electron. It's like a tug of war. And sometimes you're going to have a bigger person or a bigger, stronger atom on one end of the rope pulling. And so it's going to pull the electrons more towards it. And so that is electronegativity. So the more electronegativity you have, the bigger the pull on the electrons that you have. And so as you move across and up your periodic table towards this corner, your electronegativity increases. So atoms down here like fluorine, fluorine is going to pull the electrons of a shared bond towards it and away from the other atom in the compound. And so when you have some compounds that are not shared, the electrons are not shared equally, we actually call this a polar covalent compound. And a polar is something that has a stronger pull. If you think of our north poles, those actually have your magnetic pull to it. And so let's take hydrogen and fluorine as an example. Fluorine has very high electronegativity, so fluorine is going to win that tug of war for electrons. Even though there's a bond here, they're pulled more towards the fluorine. Comprehension check question number 6 gives me 5 elements, and it wants you to put them in order, smallest to biggest of atomic radius. So I am looking for the smallest, and so if you'll remember, we said the smallest atomic radius is on that direction. So I'm going to try to locate where all of these are on my periodic table and see which one is the closest towards that corner, and that's going to have the smallest atomic radius. So we have gallium, which is here. We have potassium, which is all the way over here. And then we've got bromine down here. Arsenic, scandium, and potassium are going to be your bigger ones because they're closer down here to the largest atomic radius. And so I'm going to be trying to find the smallest first, which is either going to be gallium, bromine, or arsenic. And if you'll look at where gallium is, arsenic, and bromine, bromine is the closest towards that corner. So it is going to actually be the smallest atom. Now the next one you're going to come around is you have arsenic. And your next larger one is gallium. And then we're going to compare potassium and scandium. Well, scandium is going to be smaller and then potassium is larger. And this is the order of smallest to largest of atomic radius. Question 7 wants us to put these elements in order of electronegativity, smallest to highest. So my most electronegativity elements are going to be on that corner again. So to start with the smallest electronegativity, and these are elements that don't pull electrons to them very well, I'm going to look more towards the ones that are closest to this corner. So I have on my periodic table, I have acetine, iodine, and they're all down here, chlorine, bromine, and fluorine. And so since up at the top is the most electronegative, the furthest down is going to be the least. And so the very bottom one, the acetine, is going to be the least electronegativity, and it's going to work its way up the periodic table. And so this would be the order from the least electronegative to the most electronegative. Before we move on to question 8, I briefly mentioned polar covalent molecules, and we're going to also talk about purely covalent. So covalent part of these terms just means they're sharing electrons. Polar is an unequal share. So these are going to be compounds where one atom is more electronegative, so it pulls the electrons to it. Purely covalent are going to be compounds where if they're having the tug of war between electrons, they're going to be having sharing the electrons equally. So for question number 8, it gives you a compound and it asks you to tell, is it polar or is it purely covalent? We cannot do that unless we first draw the Lewis structure. So the compound they ask us to do this for is, let's check to make sure it is covalent. We have nitrogen and fluorine, both nonmetals, so it is a covalent compound. If I were to name this, I would say nitrogen trifluoride. So let's draw the Lewis structure of it. I'm going to put nitrogen in the middle, and nitrogen has the 5th column, so it has 5 valence electrons. Now I'm going to add in the fluorines. I'm going to go ahead and put in the fluorines on the sides that don't have bonded electrons. I don't have enough magnets for that, so I'm just going to use pink dots. Fluorine is in group 7, so it has 7 valence electrons. And when I do that and draw in all my electrons, I can see that there's going to be a bond that forms here, a bond that forms here, and a bond that forms there. Now, fluorine is further towards this corner than nitrogen, so it is a more electronegative element. And so fluorine is gonna, of this bond, pull more of the electron towards it. So it's asking, is it purely covalent or polar covalent? Well, fluorine has a bigger tug than nitrogen on that electron. So this is a polar covalent compound, or these are polar covalent bonds in the compound. And the other part of the question asks, where is the slight positive charge and where is the slight negative charge? Well, the fluorine is going to be pulling the electrons to it. So all the fluorines would be slightly negative. We wouldn't actually put a negative. All the fluorines would be slightly negative. And since they're pulling the electrons, the nitrogen is going to be slightly positive. Question number 9 lists the electronegativity of 3 atoms. There's no units on these numbers. It's just a number that they're kind of using to rank the electronegativity of these atoms. The higher the number, the greater the pull on the electrons. And so we are given it for sulfur, chlorine, and iodine. And if you'll notice on the periodic table, chlorine is closer towards that corner, so it should have a higher electronegativity. So the question is wanting to know which 2 of these combinations would produce a polar covalent bond. Now, polar covalent bond is a bond where they are not sharing the electron equally. So if I took sulfur and iodine and I put them in a compound, sulfur's pulling about 2.5 and iodine's pulling on the other side of the tug-of-war rope at 2.5, nobody's going to be able to pull those electrons. So sulfur and iodine are not going to make a polar covalent bond. But if I were to put chlorine with sulfur, chlorine is going to pull more, so it would make a polar covalent bond. The other polar covalent bond you could make would be chlorine, sorry, it's messy, and iodine, because chlorine, once again, is going to have a bigger pull on those electrons.